I wish you a successful course and a great journey into the amazing world of nanotechnology and nanosensors. Nano is derived from the ancient Greek nanos, which means dwarf. Today, nano is used as a prefix that means billionth or a factor of 10 to the minus 9. Coupling the word nano with the unit meter brings the term nanometer, which actually indicate a unit of spatial measurement that is 1 billionth of a meter. With this in mind, we shall define nanotechnology as the science, engineering, and technology conducted at the scale that range between 1 to 100 nanometers. The idea and the concept behind the nanotechnology started with a talk entitled "There is a Plenty of Room at the Bottom" by the physicist Richard Feynman at the American Physical Society meeting at the California Institute of Technology, Caltech, in a meeting that was held in 1959. In his talk, Feynman described a process in which scientists would be able to manipulate and control individual atoms as well as individual molecules. Over a decade later, Professor Norio Taniguchi coined the term nanotechnology during his explorations and research in the field of ultra-precise machining process. However, practicing the modern nanotechnology began only in 1981 when the scanning tunneling microscope, which basically could see individual atoms or could see individual molecules, was developed and used. To demonstrate the length scale of the nanometer, I will present first the units or measures used in our daily life. If we cut a meter into 10 equal pieces, then each piece would be 1 centimeter in size. This is equivalent to the size of your pinky finger or a sugar cube. If we cut a centimeter into 10 equal pieces, each piece will be 1 millimeter. A cent coin is approximately 1 millimeter thick, and a grain of sand ranges from 0.1 millimeter to 2 millimeter in size. Objects as small as millimeter can be seen with our own eyes. However, when things get smaller than a millimeter, it gets hard to see them with just our eyes. If we cut up a millimeter into 1,000 equal pieces, each piece will be a micrometer. In other words, a micrometer is equal to 1 millionth of the meter. For example, the diameter of hair is about 40 to 50 micrometers wide. Red blood cells are 6 to 10 micrometers in diameter, and many types of bacteria typically measure 5 to 20 micrometers in diameter or in size. Things on this scale usually cannot be seen with our own eyes, but rather can be seen with a magnifying glass or with a microscope. If we cut a micrometer now into 1,000 equal pieces, then each piece will be 1 nanometer. In other words, a nanometer is equal to 1 billionth of the meter. When things are small as the nanometer, you cannot see them with your own eyes, or even you cannot see them with a light microscope. Objects this small require special tools of imaging. Things that have a nanometer scale include viruses, which have a characteristic size of 30 to 50 nanometer, DNA, which have a diameter of 1 to 2 nanometer, buckyballs, which have characteristic size or diameter of 1 nanometer, and also carbon nanotubes, which have a characteristic diameter of 1 nanometer. In this context, I would like to clarify that atoms are smaller than a nanometer. Actually, one atom measures 0.1 to 0.3 nanometer, and this of course depends on the element that is examined. Now I will give you some examples for objects from our daily life that are measured in nanometer. 1 inch is equal to 25.4 million nanometers, and a sheet of paper is about 100,000 nanometer thick. A human hair measures roughly 50,000 to 100,000 nanometers in diameter, and please note that your fingernails grow 1 nanometer every second. It is acceptable that a picture is worth 1,000 of words, and that a video is worth thousands of pictures. Therefore, I will aid with the presented short video to further demonstrate the meaning of nano. Of course, I will give the girl in the video the privilege to talk on her behalf.
Hey, do you know what nano means? It means small, very small. It is 1,000,000 times smaller than the smallest measure on a ruler. If you want to get an idea of how small a nanometer really is, you'll need to take a piece of hair from your head. Go on, it won't hurt. Got it. Now take a good close look at that strand of hair. Not much to look at, is it? If we were to shrink you down, smaller than the smallest thing you can see with the naked eye, you will find that your piece of hair starts to look a lot more interesting. You are now about the size of a red blood cell. Your strand of hair is a massive tree compared to you. Even at this size, you're still about 1,000 times too big to be considered nano. To get you down to the nanoscale, we will have to shrink you to about 100 nanometers tall. Hey, where are all the lights? You are now smaller than the wavelength of visible light. You are practically invisible. But for the sake of demonstration, I think we should turn on some lights. At this size, the red blood cell is 1,000 times bigger than you are. It is like an enormous stadium. Welcome to the nanoscale. You could probably hold a common cold virus in your hands quite comfortably now. The rhinovirus is only about 30 nanometers across and is nearly impossible to see next to the red blood cell. A red blood cell is too big to be considered nano. However, it's made up of all kinds of nanomaterials. If you were to look close enough, you would see that the outer walls of the cell are stabilized by a flexible, mesh-like protein skeleton. The bars and connectors that make up this mesh are considered part of a nanomaterial. Without these reinforcing nanostructures, the cell would be much more fragile and not nearly as flexible. It wouldn't stand a chance in your body. Everything is made up of nanomaterials. Nanomaterials are an arrangement of molecules and atoms that, when combined, create stable building blocks that can be made into larger, more complex materials and structures.
After this demonstration, I will give right now an example for the importance of miniaturization ability of the nanotechnology. As such example, let's have a look on how cell phones developed from the bulky walkie-talkie to today's miniaturized architecture. In 1985, mobile phones used to look huge in size and with a pretty long antenna. On the other hand, in present, we have the smartphones, which are becoming a computer, GPS, radio, and actually our lifeline to the internet, and still be able to fit our pockets. With the help of nanotechnology, mobile phones will be further evolved in terms of the performance and features, and would include, for example, augmented reality, flexible screens, in-built projector, seamless voice control, three-dimensional screens and holograms, and of course it might include also remote medical diagnosis features and many more features. Nanotechnology in one sense is the natural continuation of the revolution that we have witnessed over the last decade, where millions of emitter electronics, which we call usually microelectronics, became commonplace, thus enabling the construction of higher quality of materials and devices and many more applications on equivalent or even smaller areas than we have knew previously. So far, the miniaturization ability of the microelectronics allowed the integration or placement of thousands of chips into an equivalent area. Further miniaturization with the help of nanotechnology would allow putting millions of currently available electronic devices over an area that is less than few millimeters over few millimeters. In a constituent example, a team from the Technion Israel Institute of Technology leveraged the power of nanotechnology to engrave all the content of the old testimony on a piece of silicon that is less than 1 millimeter by 1 millimeter, as could be seen by the image in the bottom right of the screen. One of the parameters that is tightly connected with the miniaturization and nanotechnology is termed surface-to-volume ratio. This parameter is of fundamental importance in the applications involving chemical catalysis and nucleation of physical processes. Usually, surface area to volume ratio increases with the decrease in characteristic dimensions of the material and vice versa. Therefore, as the material size decreases, a greater portion of the atoms are found on the surface compared to those found in the bulk or inside the same material. As a growth and catalytic chemical reaction occurs at the surfaces, therefore a given mass of nanomaterial will be much more reactive than the same mass of material made up of larger particles. It is also found that materials which are inert in their bulk form a reactive when produced in their nanoscale form, and therefore they can improve their properties. To demonstrate the relationship between the miniaturization of the materials and the surface-to-volume ratio, let's consider a cube made of a silicon with a characteristic size of 10 nanometers. In this case, the number of the unit cells in this nanocube is estimated by 6,250, which is actually equivalent to 50,000 atoms. On the other hand, the number of the unit cells that are located on each face is 340, thus resulting in 680 atoms on each face of the nanocube and 4,080 atoms on all faces of the nanocube. Dividing the number of the atoms available on the surface of the nanocube, namely 4,080 atoms, by the number of the atoms available in all parts of the nanocube, which is basically 50,000 atoms, bring to the conclusion that around 10% of the atoms in the nanocube are located on the surface. On the other hand, if we apply a similar consideration with a piece of silicon of 10 square centimeters and a thickness of 1 micrometer, this leads to the conclusion that only 0.03% of the silicon atoms in this structure are available on the surface. Therefore, nanomaterials have a much greater surface area per unit volume compared with the larger particles. Actually, this leads to nanoparticles that are more chemically reactive. This is so because the molecules at the surface of the material don't have full allocation of covalent bonds and are in energetically unstable state. Since many more molecules allocated on the surface are in energetically unstable states, nanomaterials and more reactive compared to the microscale or to the macroscale materials. With the high reactivity, almost all types of nanomaterials are capable of catalyzing reactions, and free nanomaterials tend to agglomerate into bigger particles. Owing to the specific physical and chemical properties of the nanoparticles, they are expected to interact with substances such as proteins, lipids, carbohydrates, and nucleic acids that present in food, biological, or during desalination processes. Other applications of such feature include drug delivery, clothing insulation, and many